So next we'll look at electrons. So far we looked at the atoms in general. We saw, the Rutherford said there's electrons around the nucleus, but he could not say where these electrons are. Uh, uh, but then with the development of quantum mechanics, okay, we could actually, it was Niels Bohr who first, showed that um, electrons are there at specific spaces where they're very stable. They would not basically come down onto the nucleus and get annihilated. But in order to understand quantum mechanics, we have to understand light. And you might wonder why. Because light interacts with the atom or the electrons, okay? And when they interact, the electrons get excited and go to another level. And from the absorption of light, we can get information as to where the electrons are. And once you get those data, scientists try to explain that why electrons are going from one discrete level, one definite level to another, not just going anywhere, but there's a definite places they're moving. And that gave them the first indications that electrons are at definite places or definite levels within that. It's like uh, within the atom. So it's like our floor in a building, first floor, second floor. Okay, so you can be on the first floor, you can be on the second floor, but not in between somewhere. Okay, so this is called quantization of electrons. So we look at this and quantum mechanics. So let's take a break, okay? And we'll come back and look at this. So this is kind of a different, you know, uh, kind of discussion involving a new idea, which is the idea that that energy is quantized, that the energy has discrete values. It's not like a wave, continuous wave that we used to know so far. Okay, they have a definite value, and that's the birth of quantum mechanics. And we use quantum mechanics now to explain the behavior of atom and the placement of the electrons. So, as I said, in
Yes.
order to understand the electrons, you have to understand light. Now, light is an electromagnetic radiation. Okay, so now if you look at, this is a rainbow. Now, if you look at the rainbow, there's the visible portion of the light that we see. Okay, uh, now you can see these colors, splitting up. So the white light is actually made up of all these 7 colors. Okay, now so this is just the visible portion, but if you look at the whole spectrum, it constitutes like our microwave, radio wave, and all those. Okay, is a total thing is called electromagnetic spectrum. And now, so the colors that we see are basically the visible, and then the X-ray is also there, the UV is also there, but we don't see it. Okay, uh, and if you look at the classical view of radiation, it's like this way. Okay, now velocity of light is constant. Okay, uh, and the velocity of light is given by we say c is the velocity of light. Velocity of light is equal to lambda is the wavelength, okay, and multiplied by nu. So this is what we call the wavelength, means length of one wave. So that varies, but the product is constant, which is the basically the velocity of light, and we say lambda, and the frequency is how many waves are passing a given point in 1 second. So we say frequency. So this is getting recorded, I guess. So frequency, you can always go back and look at it, okay? And this is called nu. So C equal to lambda nu. And this is a constant. C is the velocity of light. So if you look at it, you have this wavelength, larger wavelengths, we say radio waves. and then comes the microwave, then infrared, okay, then our visible region, ultraviolet. So it is getting shorter and shorter. That means wavelengths are getting shorter, frequency is increasing. And if you multiply, it will become C. So you have to know basically, the arrangement of these waves. Don't need to know the exact numbers, but the arrangement that the larger waves are radio waves, the microwave, then comes infrared, ultraviolet. Okay, we have the visible in between. So this is the visible, uh, and then comes the ultraviolet, X-ray, gamma ray. Okay, so gamma ray is the most highest frequency. Now the energy, quantum mechanics says that energy E is equal to h nu. So h is Planck's constant multiplied by nu. Okay, so the frequency this is a constant term. So energy is proportional to frequency. So if the frequency increases, energy increases. So gamma ray are the most energetic rays, and they can cause the most damage. So you don't want the UV light. That's why, because uh, if there's too much of UV in our sun ray, then that causes skin cancer. Okay? The skin damages. X-ray we know can penetrate. We take X-ray pictures. Okay, and the gamma ray are even worse. They are more energetic. So this is the ways the energies are and the frequencies are. So you have to know this sequence: radio wave, microwave, infrared, visible. Now within the visible, the red is greater wavelength, and the violet is a shorter wavelength. Okay, so this is how the electromagnetic radiations are basically positioned in the electromagnetic spectrum. So the electromagnetic spectrum shows the arrangement of wavelengths of electromagnetic radiation. The visible range is only 700 to 400 nanometer. Okay, so we know, nano. So nano is 10 to the minus 9. So 10 to the power minus 9 meter. Okay, so that's our uh, range up to which we can see, and rest we don't see, but they are there and they cause damage. Now, so when you take this, you know, say light, the general light that is coming, and you basically pass it through with a prism, you see this kind of rainbow color. Okay, and this is what we call continuous spectrum. So continuous, because there is no gap in between. Continuous spectrum. Now, if you now we can excite atoms. So we can excite atoms. So when you say excite atoms, we basically take the vapor of the atom and put it to high voltage, like sodium lamp. Okay, we know sodium lamp, neon lamp. Okay, so what happens is whenever you are exciting, the electron basically jumps to higher levels, and when it comes down, okay, it gives this excess energy as light. Okay, so we can see the corresponding light for that atom. Now, if we analyze that light, okay, through prism, instead of seeing discrete spectrum, instead of seeing continuous spectrum, we see discrete lines. So each lines means discrete energy, because E equal to h nu, each frequency corresponds to one energy. Now, what that tells you is that when the electron is coming down, it can only come down at discrete places. Okay. And so from there, scientists concluded that the energy levels within the atoms are fixed, and we say quantized. Okay. So there are discrete energy levels within the atoms. So electrons cannot be at any place. They can be at certain places, like the steps of a ladder. Okay, so we say energy levels n equal to 1, 2, and so we say energy of the electron is quantized. Okay, that means it can only have specific energy values. So this was, initially done by Niels Bohr. Okay, so it's like this ladder. Okay, so n equal to 1, n equal to 2. So electrons can be in n equal to 1, n equal to, and not in between. So this is what we call the energy levels. Okay, so we don't want to get to the mathematical, all these complications of this thing. We just, we'll get the take-home message here. So uh, if you think of uh, inside the atom, the discrete energy levels in which the electron belongs. Now, how do you know about them? We excite the electrons by, usually by high voltage. Electrons go to high energy level when they get excited. Okay, and when they come down to lower energy level, they radiate that excess energy. And that is what we see at discrete lines. And because this level, the difference is definite, we get a definite frequency. Now, from these experiments, scientists concluded that there are discrete energy levels within the atoms. Okay, and they call them n equal to 1, n equal to 2, like this stack, book stack. Okay, and in each of these energy levels, you can now put electrons, and it is said the number of electrons that you can put is 2n squared. That means in n equal to 1, I can put 2 electrons. In n equal to 2, I can total maximum put 8 electrons. In equal to 2, 18, and so on. Okay. Now, so if I have hydrogen, so hydrogen, these are the n values. Okay, n equal this is n equal to 1. Okay, helium, uh, in this n equal to 1, the first level, I can put 2 electrons. Now, that means n equal to 1 is full now. I cannot put any more electrons here because if you see here, there's the maximum capacity 2. Okay, so the next electron has to go to n equal to 2. And subsequently, 8 electrons can be filled up in n equal to 2. So if I give you an atom then, like lithium, okay, when the total number of electrons 3, so the first energy level will take 2, and the second one will take 1. Okay, for beryllium, 2, 2. So we write it like this: 2, 2. Okay. Uh, that means n equal to 1 is 2, n equal to 2 is 2. So for neon, I write it as 2, 8. Now, for our course, we have to do only this much, but there are final lines and there are final divisions yeah, within these energy levels, because you can easily see that 8 electrons cannot be at one place because they're going to repel each other. But for our course, we'll just stick to this much for now. Now, when the second energy level is filled up, you start filling up the third. Now, after period number 3, it goes to period number 4. So we'll look up to calcium for now. So this is the n equal to 3, and basically you count it with this one. Okay, so it fills up the fourth level 2 electron and then comes back to 3. Okay, to fill up the rest. Okay, so this actually belongs to n equal to 3. But for quantum mechanical reason, it goes to 4, 2, and then comes back to 3 again to fill up this rest 10. Okay, and that's why these tensor metals appear here. So if you see the electronic arrangement, it will be clear. So n equal to 3 total can take 18 electrons. So what happens? It takes 2 here. Uh, so initially it will take 8, then goes back to 2, and then comes back and take the rest 10. And the switching happens because of quantum mechanical reasons. But for now, just memorize it like that. Okay. So we are not dealing with the actual quantum mechanics here. So see, after filling up 8, it goes and fills up the fourth. But the total in third, it can take 18. So after filling up the fourth, it comes back to 3 again and does the rest. Okay. And these are our tensor metals. This is the maximum number of electrons that can be contained, and you see 2, 8, 18, 32. And then in actual practice, even though it is allowed to take more, so if you do 2n square, so this is 2 into 3 square, right? So that's 18. And then 2 into 4 square. 2 into 4 square means 16 multiplied by 2 is 32. Now we actually see that at higher levels, it cannot actually put that many electrons, and so it basically remains at 32. But we can actually explain all the way up to fourth level how the electrons are filling up. So if you write the electron arrangement here, we write it like this: 2, 6, oxygen has 8. Okay, so 2, 6. When it comes to phosphorus, is basically 15. Okay, so 2, 8, 5. And when it comes to calcium, 20, 8, 2, 8, 2. So let's say vanadium. So vanadium will be 23. Scandium, titanium, vanadium. Okay. So then this would be 2, 8, 8, 2. Okay. 8, 2. But after filling up this 2, it will come back and fill up the rest 3 here. It will start to fill up the rest of it, because third level can take to 18 electrons, so it can fill 10 more after 8. So why it goes to 4 and then comes back to 3 again, that's a different reason. So will not explain it here. Okay, but for now this is what we understand by electron arrangement. Now what you see here is the last cell. If you look at the last cell, the number of electrons that you see, they are called valence electron. So valence electron is the number of electrons in the outermost cell, and that is equal to the group number in the periodic table. Okay, so now we can see that electron arrangement reflects the periodic table. Okay, so write the electron configuration for the following elements. All right, it's basically done. So let's do it here. Okay, so you have carbon, and carbon is 6. So how do you write carbon? So first cell is always 2. How much for the next?
4.
4. So carbon will belong to group 4. And if you look up in the periodic table, you will see that is in group 4. So silicon would be 14. So 2 next cell is 8.
8.
And
2, 8, 4.
4.
4 again. So silicon is also in group 4, just below carbon in the periodic table. Okay, oxygen is 8. So how do you write oxygen?
2 and 6.
Yeah, so oxygen will belong to group 6.
Group 6.
And nitrogen is 7. Okay.
So 2
So
and 5.
2 and 5. So nitrogen will belong to group 5, and it will have 5 valence electrons. So that means the outer cell of nitrogen will have 5 electrons. Now quantum mechanics says that everybody wants 8 electrons, and that is the basis for activity. So when the 8 electrons, they're inert. So if you look at group 8, they are inert. We say noble gases. They do not want to react because they all have 8 electrons. And when elements react, they want to get 8 electrons. Okay, so you can see oxygen can get 8 electrons if it can accept 2 electrons. That's why it behaves like a non-metal. And when it forms a compound, it gets a charge of 2 minus. Okay, because if it takes 2 electrons, that becomes 8. Nitrogen forms a nitride, N3 minus, because 5, yeah, 3 electrons to it, it becomes 8. So we kind of, we can see now the elements, why the elements behave the way they behave by looking at the periodic table and the electron arrangement. Now, The other thing is trends in the periodic table. Very important that you understand the period, because periodic table is like, if you look at the periodic table, it tells us a story. So it has many information regarding elements and the activity. So if you understand the periodic table, you can predict the reactivity, why they react the way they react. Okay. Now, one of the important thing about the reactivity is, there's electrons and there's protons at the center. Okay. So this is our protons, the nucleus, and this is the, let's say, electron around it. Okay. And let's say here is the electron. Okay. Now the electrons, if they're closer, they held more tightly. It will not want to lose that electron. Okay. And if they're far away, it will want to lose. Then it'll behave like a metal. Metals lose electron. So if the size of the atom increases, they will behave like a metal. So if you see this, this is the size, okay, atomic size. Atomic size increases as you go down the, group. So as the number of period increases, atomic size increases. Why? Because you're adding cells, right? So you are continuously adding cells. You have, one cell here. So this is one cell, and then in the next one you have two cells. Okay, n equal to 2. So you have two cells. The size increases. So as the size increases, the atoms get bigger and bigger, and the metallic property increases because the electrons are far apart, easy to lose. So the metallic. So if you know the size, you can basically predict the properties. So as you go down the group, the atomic size increases because you are adding cells, and the electrons are far away, so they're getting more and more metallic. So potassium is more metallic than lithium. Okay. Now, along the period, what happens? You are in the same cell, and you are adding proton into the nucleus, and that, shrinks the atom because the electrons are now pulled more by the nucleus, and the atom sinks. So you can see the atomic size decreases as you go from left to right. And if it decreases, that means it is holding on to the electron more tightly. It doesn't want to lose. That means it's a non-metal. Rather, it will take in an electron there. Okay, because the nucleus is very close to the outer surface. So they behave as non-metal. So as you go from left to right, the atomic size decreases and the elements become more non-metallic. And if you look at it, it's like a diagonal arrow, right? So as you go down, it increases. As you go from left to right, it decreases. So the smallest one is at the upper right-hand corner. And as you go, diagonally here, that is the increase of size. So as you go down, it increases. As you go from right to left, it increases. So we say diagonal arrows. So kind of nice. So we can see a pattern here now. Okay. And when you look at the size, these following things, atomic size, ionization energy, metallic character, they all follow a trend. And the trend, this is the atomic size trend. Now, if you know the atomic size, you can explain everything else. So that means if the atomic size increases, the metallic character will increase. Ionization energy is defined as the energy required to take the outermost electron. So greater the metallic behavior, the less energy it will take because it's far away. So you have to put less energy to take that outermost electron. So the ionization energy will gradually decrease as the metallic character increases. Okay. So this in gist is basically the periodic trend. Okay. Now, the group number, valence electron, as I said, valence electron is basically the outermost energy level. The number of electrons is the outermost energy level. And when you look at the group number, the group numbers are equal to the valence electron. So if I look at a group number, I can tell, like nitrogen has 5, I know it is in group 5. Okay. So we are now kind of more systematic here. We can predict. Okay. And these are some of these, so if you look at 18 or 17 is chlorine. Okay. So 287. Okay. That is how I would write the electron configuration. Okay. And that's why it has 7 valence electron. If you look at sulfur, it's 286. So that's why it is in group 6 and has 6 valence electron. So this phosphorus 285 and so on. Okay. Now you look at the inert gas, which is, so inert gases are like neon, argon. So this is argon here. So if you look at argon, it is 18, that means 288. So it has 8 valence electron in the outermost shell. It will belong to group 8. And because it has all 8 electrons in the outermost shell, it is satisfied. So they are inert, they are noble gases. Now, the valence electron, are important to us. Why? Because they're in the outermost shell, they are the one that interacts with, other things, other atoms. So valence electron, the properties of the elements basically depends on the number of valence electron. So elements having the same number of valence electron behave similarly, and that's why they belong to the same group. And this is a way of depicting, the valence electrons systematically. Okay, so the 3 electrons. So you will think of it like the side of a square. Okay, so this is like the side of a square, and you put 3 electrons here. If the 4 electrons, if it is like carbon, okay, I would put, we try to put it like in artistic fashion so that it's easy to count. Okay, now if there are more, like if I have nitrogen, 5 electrons, then I'll write it like this. 2 as pairs, because now, and then 1, 2, 3. So when we have argon, argon has 8 electrons. I'll write argon like 1, 2, 3, 4, 5, 6, 7, 8. So you try to do it like a pair, like a systematic way, okay? So that is aluminum. Now these are other ones, magnesium. Either one is correct, okay? Like magnesium has 2 valence electron, so you can do it either way. So all of them are correct. But you draw it as if they are on the side of a square in a systematic way. And these are, these whole examples all the way up to krypton. A lot of examples here. Okay, so let's write the electron dot symbol for each of the following. Chlorine. So how to do that? First, you go and look at the atomic number of chlorine. So what is chlorine? Is 17. Okay, good. And then write the electron configuration.
2, 8.
Okay.
That's 10, 7. No.
7. Good. So how do I write the electron dot formula for chlorine?
So it's going to be 7.
7 electrons. So I have to write it like 1,
1, 2,
2,
3, 4,
3,
7.
4, and then I'll pair up. So
2, 3,
1, 2, and then 3. So these are my 7 electrons, and this is the electron configuration, electron dot symbol, electron dot symbol for chlorine. Similarly, we can do carbon. So carbon has 6. So atomic number is 6, and then 2
and 4.
4. So we can put carbon like 1,
4,
2,
7,
3, and 4. So nitrogen is actually 7. So 7 means 2 and 5. Okay, so nitrogen, we write the symbol here, and then 1, 2, 3, 4, and 5. So it really doesn't matter which one you make, which side you make 2 electrons. You can make it bottom here or on the sides, as long as it is there. Yeah, so see, it's on the side. It's still correct. So the periodic, trains that I discussed, okay, is just repetition of that. Atomic size is basically the radius, okay, from the radius of the atom, which is the distance of the nucleus to the outermost electron. And if you look at it, the trend is basically as you go down the group, it increases because you're adding extra cells. And if you go along a period, so you are keeping to the same cell, but you're adding protons into the nucleus. Okay, so that means the nuclear charge increases. That basically pulls the electron inward, and the atomic size decreases. Okay. As you go from left to right, atomic size decreases. From right to left, it increases. And again, these are diagonal arrows. Okay. Okay. So if you go this way, it will increase. That's why it's a diagonal. If you go this way, it will increase. Now, ionization energy is these electrons are held by the nucleus. So in order to take this electron out from the atom, you have to give energy. So closer it is to the nucleus, harder it will be to pull the electron out. That means more energy. So if the metallic character increases, that means it is easy to lose the electron, easy to take away the electron. So as the atoms become more metallic, the ionization energy will decrease. So this is how we depict the ionization. Okay, you give energy and the you have the Na plus, so you create an ion in the gaseous state. So we say this is a kind of standard way of saying that if I have sodium as a gas and the gaseous state, the amount of energy that I have to give to take the outermost electron out is the ionization energy. Okay, and the ionization energy decreases as the distance from the nucleus increases because it is less tightly bound. And so you can see as you go down, okay, the ionization energy decreases. So it says decreases, not increases. Okay? Even though the arrow seems like it is increasing, it is decreasing. And the ionization energy increases as you go from left to right. Why? Because the atoms are getting smaller and smaller. It's more tightly bound now. So non-metals have very high ionization energy, whereas metals have very low ionization energy. So by looking at the ionization energy, I can tell whether an element will behave like a metal or a non-metal. There's another way of looking at it. So if you look at the metallic character, an element with metallic character is the one that loses electron easily. That means it will have low ionization energy. And you will see them at the left side of the periodic table. And the non-metals in the upper right-hand corner. Okay. And they do not lose electrons easily. So now we can basically understand the position of the elements in the periodic table. Okay, why the periodic table looks the way it looks and the behavior. The periodic table, as I said, tells a lot of stories. So looking at the periodic table, you can tell whether element is a metal or a non-metal, how many electrons it has on the valence shell, whether it will be reactive or not, or if it reacts, how it will react. Okay, and then the family of elements that will react very similarly. So if I know one, I can predict the rest. Okay, so very, very useful thing in chemistry, the periodic table. So these are the metallic characters, how they're going to increase from top to bottom and from left to right. It decreases. Okay, metallic character. And if you look at the ionization energy, then ionization energy decreases as you go down. Okay, you see the ionization energy decreases. So there's a pattern here. So initially you have to write it down. Okay, get the idea. So the summary, the trend, that is, saw so far, you have the valence electron, top to bottom within a group, they remain the same. So all elements in the same group, they have the same number of valence electron. And that's important because that gives the property for that group of elements. So if you look at group one, all of them has one valence electron. And they lose one electron, okay, when they form compounds. So when you write formulas, this becomes very important because that makes your life easier. You look at the periodic table and you can write the formula for the ion and you can form the compound from that ion. Okay, right, with the right formula, just by looking at the periodic table. So ionization energy decreases, from top to bottom, increases from left to right. But best is, you remember the size and try to relate that logically, okay, instead of looking at them as individual things, because they are all related to size. Uh, so metallic character increases from top to bottom and decreases from left to right. And then they're all related to the size. Now, given the following elements, answer the question, which is the largest atom? You have carbon, nitrogen, chlorine. So if you look at the question in the periodic table, so you have to look at the periodic table now. Okay. So if you look at the periodic table, you have carbon, you have nitrogen, and then you have chlorine. Okay, oxygen and chlorine, and then right here you have silicon, you have phosphorus, and you also be able to write it like this once you keep studying the periodic table. Okay, like the way I'm doing. So it's nothing great I'm doing here. Okay, you get used to it. So as I said, the size decreases. Okay, so that means it increases along this direction, and it increases along this direction. The size. Okay, so which is the largest atom here? So if I am to put them in order, the largest is chlorine. Okay, so that is the largest, uh, and then the next one. This is inequality. Means larger is chlorine, and the next larger atom here would be carbon, and then nitrogen. So nitrogen will be the smallest. And if I have chlorine, chlorine will be even smaller. And which has the highest ionization energy? Highest means the smallest will be the highest. So ionization energy highest will be nitrogen. So if I know the size, I can tell that nitrogen will be the highest. Which one belongs to group 5? Okay. Now we need to write down their uh, you know uh, electron configuration. So now if you look at the periodic table, you can always figure that out. So nitrogen belongs to group 5. Okay, so this is again nitrogen. Okay, and it has 5 valence electron. So periodic table basically tells us a lot of things there. Okay, just by looking at the periodic table. So and that will be given to you during the exam, but you have to know how to analyze that. Okay.